but the camera certainly thinks I am. An amazing start. Maybe? Yes. All right, so we are live. Today is February 27th, 2024. We are on week 8 of CSE598. Let's make sure Twitch works today. Does Twitch work? Twitch does work. All right. So our topic this week is dynamic allocator exploitation. This is kind of heap 2. We did heap 1, which was just the T-cache 2 weeks ago. And then this past week we did primitives and memory mastery, which was mucking about with the T-cache, race conditions, a little bit of this, a little bit of that, and kind of seeing what we can do with these arbitrary reads, arbitrary writes. This week we're going to go a little bit deeper into the heap. So memes. It turns out that the number one complaint about the last module is still race conditions. I don't understand why, because I like race conditions. Race conditions make sense to me. However, it seems to be a big complaint for the class as a whole. The one on the far right I liked in particular. I think that was the first one that got posted. It's just like, oh, yes. But it's a race condition. Other memes, demangling. So demangling and safe linking is, part of the T-cache module, the last 4 levels. Hopefully everyone has gotten to there now. And it was all of the previous module, was how does safe linking work? How do we do this demangling? And if you can't do that, you have a bad time. I think this one is a dig on me, because that was what I did in office hours, was I missed a paren. If not, and you missed a paren, don't feel bad. I definitely did it, and it's now forever immortalized on the internet. And then kind of I like this one, which is just the takeaway there, right? I don't understand demangling, just steal the function that Robert wrote. No, you have to understand the math. I think it is important to understand the math, right? Because I don't know the function, but I can do the math to get to the function. And then once you know that you can derive the function, you never have to do it again because you'll just steal the function. But it is important that you can do the math and you understand why it works the way that it works. This was an interesting collection of memes. I'm not sure. I have mixed personal feelings about this. Okay. As I think you're all aware at this point, we've gone through different modules. Some of them have Jan, some of them have Jan and me, some of them have just me, depending upon when in time they were made. People apparently can relate to Jan stumbling in GDB. All right, apparently I'm just too good at GDB to be relatable anymore. All right. I don't know how true this is. Right? This middle one has me kind of scratching my head, because I've done a number of these pwn.college courses, and it's cool when the community helps, but I don't know if there's a sleeper agent in this classroom that is just carrying everyone. If that is the case, I'm not mad. I just yell at me and be like, Robert, you should be more helpful, other than random person on the internet. I'm happy to have online people help, for the record. But I hope that they're not the ones carrying the course for you that are taking this for credit. But it can't be that big of a deal, because the individual here also posted the one in the upper right, where they were expecting you guys to ask for a bunch of help so that they could troll you, and then you didn't. So I'm going to take that as a sign of confidence, right? That you are figuring things out and not over-relying on helpful people on the Discord. I'm just going to give up on this camera soon. I do like the one in the bottom right. That is kind of the best thing that you could learn from going through any of the pwn.college courses, in my opinion. This is just a philosophical thing I will die on as far as what education is really about. It's not about memorizing the demangling function, right? It's not about memorizing how printf exploits work, right? The skill that you're practicing is your problem-solving ability and your ability to reason about these different types of systems, so that when you see something you haven't seen before, hopefully you can quickly begin to reason about how it works, That's really kind of what the hacker mentality is about, is just rapid problem solving and iterating on kind of the unknown. For a few of us that have made it to the current module, they have learned the joys of the deeper heap. And this entire module is set up a little bit differently. I mentioned it on the announcements for the Discord. This module is not a here's 10 levels or however many levels that are like a tutorial, hold your hand, build your own. The first couple levels are about how you leveraging consolidation to like accomplish something. And then the rest of them all say, let's see if I can grab it here. Like use an advanced heap exploiter. I don't know, some generic nothing burger. Perform an advanced heap exploit to obtain the flag. That is your hint for every single one of these going forward, right? And that is on purpose, because the design here is all of the intended exploits are listed on this how to heap repo. And we talked about primitives and kind of explored that concept in this past week. Well, this is what primitives do you have, right? You're going to get a challenge. Well, what do I control? What can I read? What can I write? Based upon that, make a mental model of, okay, this is the capabilities I have in this challenge. And then you'll map that to what you see in this how to heap repository, which we'll take a look at today. Now, if you haven't, formed a logical system of doing so, of being like, okay, I have this is what I can do, and this is what this type of exploit needs, then doing this module is very much like the image right there, where you're just going to see something on the how to heap repo, and you're just going to try and do it, and be like, I don't know, man, it doesn't work. Then you're going to grab another one and try it, and be like, I don't know, man, it doesn't work, right? And like, okay, you can probably brute force your way through it, but it's not the intended happy path. And I like this other one here, which kind of harkens back to something that Jan said in the Tcache module. Just the heap is a constantly evolving thing. And so heap exploitation is not as simple or straightforward as it used to be. And a lot of the times, if you look for information online, what you find may not be current or up to date, because there are additional things such as Tcache or safe linking, or making sure that allocations are aligned, that are suddenly new barriers and challenges. But by that same token, there are other exploits that didn't exist, right? Because you're adding more complexity. So, I said, I think in office hours, I would figure out what was going on with this schedule, right? Because as I noted before I started the stream, this right here, everything that we've done through this week is the CSE598 course, which is like the predecessor to this. And that was a full 16-week course, and we have managed to pull it off in a fine 8-week period going into spring break. So congratulations to all of you, right? Because that is an accomplishment in and of itself. But what is going on? Well, we'll touch that in a little bit here. Right now, advanced heap, spring break. So how'd we do? That says dynamic allocator misuse. That doesn't say primitives and memory mastery. Did I grab the wrong? Gosh, dang it. I grabbed the wrong image. Well, people are doing fine is the answer. The class average is a little bit lower. This number I know is accurate, and I know why these are not updated. It's because I'm a silly goose. The class average is a 92.28. I still haven't pulled extra credit again since I did last time. I will pull it again over spring break, because spring break we have the kind of that pause where nothing's assigned, so then everyone will know where they are. It's a nice midpoint. Overall, I'm good with the grade distribution. Like, people seem to be doing well. I haven't heard any complaints from anyone. So far, so good. I said there'd be no curve. There will be no curve. Logistical things. So there were some stability issues with the dojo over the weekend. It wasn't as bad as it could have been, to be honest. Connor did some magic. But there were issues. And I don't want that to be a reason why people couldn't solve this prime module. So I'll give you guys a choice, and I want you to like raise your hand, vote yay, nay. We're going to do one of two things. I can either move the due date of Primitives of Memory Mastery to the end of spring break, at which point you get 100% credit on everything that's through 310, or I can just give you a flat 1% course extra credit, and we call it good there. Personally, I think the 1% course extra credit is the better way to go. Everyone gets it. That's equivalent to about 12% of a module, which is about 2.5 challenges from the Primitives of Memory Mastery module, and then you could still solve things late for 50% extra credit. Who wants to have work over spring break? Okay. Who wants a free 1% course extra credit? That's right. It's just, let's take it, man. All right, you get it. Easy breezy. Some people do say no. I've been in this position before, and people are like, no, I don't want extra credit.
There's no curve, so it doesn't, like, even if there was a curve, it would still matter, right? If everyone gets it.
If everyone gets it, like it's a rising, rising tide lifts all boats here. Like, but some people vote against their best interests, and I allow you to do so. So spring break, as I mentioned, there is no work assigned. I'm glad that you voted to not give yourself work, because that's what I expected. This current module, I also have kind of a mixed feeling here, because I wanted to add stuff, but I didn't get to it. So, right now, it's due on, the 3rd, 4th? It's like the 1st or 2nd day of spring break? 4th? Yeah. It's due on the 4th. I'll let you guys, again, decide what we're doing. We can leave everything as is if it's due on the 4th, or we can push the due date of this Advanced Heat module to the 10th, but I get the ability to add a couple challenges before spring break. What do you think?
With the 1% extra credit?
Well, 1% extra credit's done. You're getting that. I don't care. Okay. That's a done deal. That ship has sailed. Right? This is a totally different question. Right? This is, do you really want to have spring break? Right? Or would you rather have 2 weeks to work on this, but I throw a couple more on there? No more than 2. Like, I don't have enough time to rate.
Alternatively, does it give you more time to solidify the second half of the course?
Right. No. Like, there's a pro con for me as well. I'm asking you. All right. If you have no opinion, then we'll leave it as is. It's due on the 4th. Okay. So that was easy. Believe in democracy. Okay. Because then at the end of the semester, like, if everything goes horribly awry, I'm like, hey, man, you were in on this. You were part of the decision-making process. Right? It helps me shirk blame. So, plan changes for the second half. This is what we originally had, right? We come back from spring break. We talk about Windows. We have 2 modules on Windows. There's a withdrawal deadline. I don't think anyone here should withdraw, just as a statement here, but it's on there for factual purposes. We are then going to have 2 different modules, one on pivoting persistence, one on botnets, real-world binaries, and then we had this like flexible time here at the end. This is what I've been showing you up until this point. Here is what I've kind of compromised on, or decided to change. We still come back from spring break and talk about Windows. So far so good. I know people are stoked about Windows. That's going to happen. I'm taking what was the pivoting and persistence and the botnets. I'm smashing those 2 things together because they are semi-related as far as concepts go. So it will be less quantitative challenges, right? I'm not going to it was going to be 20 and 20 and now you have 40. Like, I'm not doing that to you. Like, I will smooth it out so that it is one concept that kind of covers both of these topics in a smooth transition. And then Jan announced something earlier this year called the quarterly quiz, right? Anyone happen to catch that? I don't think he did a good job of announcing it personally. So there is something called the quarterly quiz, right? And this is something that we're trying to do on pwn.college as a whole. One of the things that we know is lacking is new content in general, right? Courses like 598 or 494, whatever it is that's kind of at the leading edge is where this new stuff comes out. And that happens once a year maybe, and it depends on like ASU scheduling and who has the time to do so. So as a platform, we have decided or announced that every quarter we will release at least one new module, like irrespective of the semester. The first one is announced on April 1st because Jan thought it was funny that it was April Fool's Day, which totally messes up our schedule. But that's what we got to do, right? So we're gonna fit it in and make this work. And that means that 3 months from now, so probably sometime in July, don't hold me to that. Even though there is no ASU semester, we will release, again, a new module on something new, interesting, challenging. And hopefully that is exciting, right? Like, I'm not the one building the quarterly quiz, for the record. I was going to compete in it, but now I have a little bit too much insight into what it is, so it wouldn't be fair. And so we're going to line up with kind of this mystery quarterly quiz thing. And so what that means is we have week 1 windows, week 2 windows. We'll have a combined persistence botnets kind of module. We'll do this quarterly quiz, right? It's going to be a crap shot. Well, I don't know if this is going to be really hard. I don't know if it's going to be really easy, right? We're gonna feel it out. That's why we got 2 weeks slotted for it. And if it's impossibly difficult, then we'll like give some extra credit and say, hey, good job, right? But it should be something fun and interesting. Question?
Do you know if we have covered all the topics in the first quiz?
So that is why I cannot compete along with you. It is in development, and then by the time it gets like a couple weeks before is when I have to make sure that you guys are properly prepared, right? It's not going to be, or make sure that the content itself ramps in a sane learning manner, right? It's not going to be like, oh, this is on, I don't know, Mac OS internals, right? Good luck, guys, right? Write Swift. Like I'm not going to do, it's not going to be that. But it may be one of the more challenging modules in the whole course, right? Because it has a different mentality into it from a design standpoint. And so it's going to be built from here's something cool and hard and difficult. And then I'm going to look at it and try and like shave it into something that is better for the course. And we'll see what happens, right? Worst case scenario, it's like impossibly difficult. So like speculative execution in 494, for example, was the final boss of 494. And nobody could solve it. And it was really, really hard. And everybody hated it. And it was supposed to run for a week and then 2 weeks. And then it ran until the end of the semester. And people still hated it and couldn't figure it out. And then I was just like, this whole module's extra credit. Like, don't worry about something completely like bombing the course from a design standpoint. If we release something and it's impossibly hard, I will make sure that it doesn't destroy you as a student for the course, right? We will adapt and we will make it work. Does that make you? Okay. I don't think it's going to be that extreme, but if I'm wrong and like we end up in that same boat, we'll make some similar judgment calls along the way. So we'll have this quarterly quiz here that's going to run for 2 weeks, and then we'll have real world binaries, which will also run for 2 weeks. And you'll note here, I still have a flex week, right? I expect that will probably get lit on fire up in Windows as we run into like infrastructure things where people are like, oh, Windows isn't loading, right? But we'll see what happens there. If we don't end up needing this flex week, then you just get finals week off, right? I imagine some of you have other classes, so maybe you appreciate that. And so that's the plan. Does anyone hate the plan? Twitch has thoughts. Twitch is excited. Oh, I thought they said scared. They're excited for the quarterly quiz. Now I'm excited too. It's gonna be some good stuff from what I have seen of it. So the plans for today. We were talking about kind of the greater heap, right? What's happening beyond Tcache. So bins or buckets or whatever word we want to use. I think the proper word is bins. Consolidation is something that happens that we didn't see in Tcache. And then this how to heap repo. Before I ramble about these three things, does anyone have any questions in particular?
The next module, or the module after this one, is going to be released during the Friday of spring break, or
The plan is whatever is on the schedule. 3/8, which I believe is the Friday before spring break ends.
cool.
That just keeps us on our 10-day kind of overlap there. If you do nothing, that's perfectly fine too. Okay. So let's start up one of these guys. I'm not going to use the demo challenge. And then, who has watched the lecture material? Yes, yes. Sort of. Okay. It's tough doing the like demos and discussions at this juncture, because you're like, you never know what people know and what people don't know. Okay. So I have made a super cool directory called Hepo. Inside of Hepo, we have a classic Robert file named do.c. Do.c is not particularly complicated. It is just an infinite loop. It's going to allow us to either malloc or free. We have 16 slots. We've seen something like this before. There is no exploit. This is literally just a toy program for us to run and then look at the state of the heap as we do various actions. Question.
For this module, are we going to still want to use pwn.college because of threads, or?
So the question is, for this module, do we still want to use pwn.debug for threads? If I recall correctly, which is always a gamble, everything is single-threaded in this module. And so for the demo, I'm going to be using Jeff, which reminds me, somebody says, I will never catch up now. I wouldn't mind an advanced kernel module. Yeah, you never know, man. Okay, which reminds me of something. Let's go. Let's see if good things happened. Did good things happen? No, good things haven't happened. It's still a lie. Following our sweet PR to make Jeff. Oh, PR has been merged. Okay, in theory, VM map works on the latest version of Jeff. All right, it's probably not updated on the dojo, but it at least works on the project. I will update the dojo this evening. Doesn't fix the threading thing, just fix the VM map thing. So separate issues. Okay, so our example code here. Pretty simple, right? Beautiful. Let's compile this guy, and then we're going to use everyone's favorite tool, GDB, to reason about it. So I could malloc into 1, and I'm going to malloc something of size 64. I'm then going to free slot 1. What do I expect would happen?
50 in T-cache.
50?
Yeah.
In the T-cache.
Yes.
Did you already finish this module?
Yes. I finished this piano later because I have rebuttal, and while I'm running the experiment, open one.
I finished it late. Oh, I finished it before class, but it was late. Oh, the horror. Yes. So as was stated in class here, that entry ended up in the T-cache. Now, I'm not going to make the same mistake I did 2 weeks ago, and we are going to use a Python script to interact with this thing, because we want to interact with more than the T-cache. Now, what if I want to... This is going to cover up my head. Do this, and then that. Can I go 2? 1, 2. Yeah, good enough. So we'll make a do.py user bin env python 3 from pound import star p equals process a.out context arch AMD64. Good old boilerplate. All right. We send line malloc 164. Now, what if I want to get beyond the T-cache? How many entries go in the T-cache for a given size?
7.
7? 7's correct. So if I wanted to fill the T-cache, what would I want to do?
Malloc and then free, or malloc 7 things, free 7 things, the same size.
Okay. So for I in range 7. We'll make this an F string on I. Do the same thing right down here. And then we will use GDB attach. Look good? We got the thumbs. That should fill the T-cache. So then if I go one more, that should be beyond the T-cache, right? So we should see the T-cache full, and then we should see
Something in fast bin?
something, okay, the claim's in fastbin. Okay. Oh, now where did we need to move do.py into Hepo? ch plus x do.py. Okay. Classic mistake. No, classic blunder. There we go. After the attach, I need an interactive or something to keep me alive. And right now, my SSH is slow. Oh, yeah. I know why. 365 deadline. They pushed it by a day. So you know what's happening, right? You know what's happening right now? They're all running D drive. I was like, why do the keys not work in the Vim? We like the Vim. Okay. All right. So now I can go heap bins, and what I see is as you describe. The T-cache is full, and I have something in fastbin. Now, what do we know about fastbin?
Unlimited number of things per size.
Right? Fastbin works pretty much like the T-cache, except it's not thread local, right? It's the caching layer for the heap as a whole. Now, we could malloc something that is large enough so that it isn't in fastbin, but it still is in the T-cache, right? We could do that. I don't know what that number is. Let's find out together.
Greater than 88.
Greater than 88. I think that slide's a lie. I think it's hex 88.
Greater than 78. Try 79.
You want 79. Okay. These are the type of things that somebody could memorize, but I just like run numbers and see what happens.
Sorry.
Hex 79.
Yeah, that's why the slide's wrong. So the slide says 88, but it should be hex 88 for the chunk size, if I remember right.
That's
Okay.
100.
I don't think scanf will accept hex numbers. So
Yeah.
136.
The 79 still.
Yeah. The greatest source of me floundering on stream is typing things that other people say, because then I stop thinking about what I'm actually doing. So what happened now? This was bigger. Where did it go?
Top chunk.
You give everything away. Okay, so the answer from the peanut gallery here was top chunk. What does that mean? What is the top chunk? It's not the word we use in our streams. The wilderness, right? So the wilderness exists at the very end. And this is something that somebody already ran into because it came up in the Discord. Let's see if I can randomly find. This will at least get me to the source. And if we were to look, where am I? I need to find free in here. I think it's lower. Okay. We see that we try and use Tcache if we can, and then if it can be, if mmapped, malloc, there's the free. Somewhere in here, it will immediately try and merge it or consolidate, right? Because if we free something and we immediately know that we can consolidate this into a bigger chunk, then that's what we do. And so that's what happens, although I don't. 4566. If trim fast bins, I don't believe that. Oh, I'm not looking at 235. For the record, the dojo is on 235. You said 4566? Yeah. 4566. Yes, that is where it is. And we see the comment there that helps us know what is going on. Consolidate other non-mmapped chunks as they arrive. And recall, like, extremely large chunks get mmap. So this is just, hey, anything that is getting freed, if we can consolidate it right away, let's consolidate it right away. And so that means that this extra chunk here that we mallocked and freed, what is right in front of it in physical memory? So you see me type heap bins a lot because I like looking at this. But there is another Jeff command, heap chunks. This is looking at the same thing, but now we are looking at it in terms of contiguous memory, where these are located, right? And so this guy down here at the bottom, it says, is the top chunk. This is the wilderness. And so that last chunk that we mallocked and freed would have been located right here with the wilderness right after it. And so what the heap decided to do was take that chunk that was freed and just combine it with the wilderness. How can we prevent that?
Guard chunk.
The guard chunk. The guard allocation. So if I malloc 1 through, or what is that, 0 through 8, and then I free 0 through 7, then I would have an allocation, but that would be sitting between the last freed chunk and the wilderness. We agree?
Yes.
Cool. This is a super critical thing to understand for doing these heap shenanigans. So now I see it is in unsorted bin because it was too large to be in fast bins. So everything that doesn't get cached in fast bins, regardless of its size, it goes in unsorted bin. Unsorted bin is just this pile of everything that gets freed. Right? And if we look at heap chunks, the reason that this is in the unsorted bin is because within contiguous memory, okay, let's get this address here, whatever it's 539605336. This guy right here, this chunk is that chunk up there that's in unsorted. And in the first instance, it was right next to the top chunk, and so they could be smashed together. But in this instance, I have this chunk right here sitting in between. And so this is preventing these two from being merged. Now, what would happen if so this allocation right here is a guard allocation or a guard chunk. And we know that it is a guard chunk because it is marked as in use. And so the previous in use of the wilderness here is discussing this allocation or this chunk, which is our guard chunk, which is what's preventing this all from smashing together. And so if I wanted to, what if I wanted to move this unsorted chunk? I want to make it sorted. How do I cause that to happen?
Call malloc a bigger chunk.
I call malloc with a big chunk, and that's right. So counterintuitively, the way to get most things to like move through the bins is first you'll need to make sure that it's not going to automatically consolidate. So have some type of guard allocation. The second thing is when you initially free it, it's going to end up in this unsorted bin. You can't move it from the unsorted bin to somewhere else until you call malloc. It's the act of mallocing where we grab the unsorted bin, this like garbage dumpster pile of here's all of the stuff that's been freed that we don't know and we don't care, right? But all of a sudden when we call malloc, we'll dig through the unsorted bin until we find something that satisfies what we need. If, when we look at it, it's too small, we'll put it in the small or large bin. And so let's do that. Malloc into, I don't know, 14's a number, and let's do like 1,000. And so now what we should see is that same chunk is now down here in the small bins. And so it was in the unsorted, where's unsorted? It was in the unsorted bins, and then when we called malloc, we looked at it and said, hey, I need something that is 1,000 bytes in size. Is this 1,000 bytes in size? The answer is no. So then we put it in the bin that it needs to be in. And so that is how things move throughout the heap. Right? Now, interestingly, what would happen if I did we do all of this, P send line, let's malloc into 10 as a number, and let's malloc something of 1,000, and then we'll send line free 10. Now what if I do this? So I'm still mallocing my stuff here out of the T-cache to get that into the unsorted bin. What happens when this big malloc happens? So we do all these mallocs, we do this. Where's this free end up?
Doesn't that get absorbed?
T-cache.
Oh. Because it does fit in T-cache, doesn't it?
It does fit in T-cache. How about that? That's too big for T-cache, right?
Does that get absorbed back to the wilderness?
Yes, I imagine it would. So if I wanted to have this large allocation, what would I need here?
Okay. another malloc after that malloc time.
Does the size of it matter?
I don't think so.
Okay. So how big of an allocation do you like?
20.
20.
The small boy up there. So
Okay. So this is our guard allocation for the big boy. This is the big boy. This right here is 7 mallocs for T-Cash. I'm not done typing. I understand that half of what I type is wrong, but you could at least wait until I hit enter to tell me so. 7 mallocs for the T-Cash, because the T-Cash accepts how many? 7. Cool. So we have our 7 mallocs through the T-Cash. We then have 1 small allocation, and then we have 1 guard allocation. Yes?
Yes. Correct.
7 plus 2 is still 9?
Yes.
Okay. All right. Got to check in here on Twitch. I like this module. It doesn't have crazy races or scripting. It's just pure understanding for the win. It is. I like this module as well. And check on time here. So, and I like having comments when you write these out, like explain what you're doing. Hey, I'm filling the T-Cash. I have 1 small allocation. And you wouldn't even necessarily, if I were to write this myself, I would probably split this out as 7 and then 1 and then explicitly state that I have this guard allocation. But this should still do the same thing here. And so what do we expect to be the state of the cache after these actions? We could just look at it, but can we reason about what we might end up with? So I fill the T-Cache. I have 1 small guy. The small guy ends up in the unsorted bin. Right here, this is a large malloc. Where are we going to look first? The unsorted bin. Can I satisfy this requirement from the 136? No. Turns out 136 is smaller than 3,000. So that means that the small allocation will get moved from the unsorted bin to the small bin. Then this guy gets malloced and freed, and if I were to do that, that would fail because that would get merged into the wilderness. So instead, I want this. Because I need the guard allocation to exist before the thing that I'm guarding is freed. That's its whole purpose, is to sit there in front of the chunk that is being freed. And so then we free the big boy. The big boy will end up in, it's not a trick question, everything goes to the unsorted bin, the pile of garbage. So the big boy goes to the unsorted bin. Then, I don't want to free him. You shouldn't free your guard allocations, like in general. Like the whole purpose that they exist is to be there. All right, and so that gets into the 3,000 in the unsorted bin. This fills the T-Cache. Then when I malloc, well, let's comment this out. Let's sanity check. I'm saying a lot of words. What we should have is our 3,000 guy in the unsorted bin. Is that what we have? We do. That's what this here is. We print decimal OXBC0. That's our 3008, right? And so we have our giant guy right there in the unsorted bin. And that is before we malloced, and we do this. What happens when I do this malloc 14,1000?
Things will get sorted into their appropriate non-unsorted bin.
What pointer am I going to get? If we know this right now. The Magic Man says, you say 6B0?
I don't know. I don't know if it shows the chunk address or the original because I use another.
But I'm allocating 1,000 bytes, and you're saying I can get 1,000 bytes from this hex 90?
No, sorry. It should be. Where is the unsorted?
Do we get the 7C0 address? Or
Yeah. So my claim, and maybe I'm wrong here. This would be great if I'm wrong. Is that it'll come from the 7C0 chunk.
does that chunk get split, or do we just get back the whole 3,000 chunk?
Let's do it. We won't get the whole 3,000 chunk. That's for sure. Okay. So what was our command here? Malloc 14 1000. How did nothing happen?
Wait, did it crash or something? Or
Where is the unsorted? I cannot find that.
Unsorted's right here.
So, what's the address? I see.
That should have caused this to be sorted and then broken this into a chunk, is what I expected.
we want to restart our program and
Yeah, we're going to automate this.
We should. I think it would split the huge one because first thing first.
Yeah, there we go.
Oh,
nice.
Okay, so it had to have been something with like the IO of me typing it, because what we see here now, I want it to work with the IO. It's way cooler if it works. Or not do.py. Let's edit do.c. And where does this thing actually call malloc? Let's printf %p malloc returned pointers index, and then we'll include standard IO. Okay. So now let's comment this out and do this all over again. We have our do.py. We are in that same state. The claim was that the address will be, depending upon whether this is the chunk of the allocation, it will be plus or minus hex 16 of this address right here. We continue. We malloc. What was my magic command?
Oh, I think you should type
14 1000.
I think you're in a weird.
I think we should switch it to the terminal one.
Oh, you want it to be up. Oh, yes. Okay. CBD0. And then where was my CBD0? We did it. It is, in fact, the same pointer. And so we saw that this was too small, and so we threw it away, and this went into the small bins. That one was too big, right? But it was big enough. And so we snapped that guy in half.
Can you check it? Like, show us.
It showed it right right here.
Yeah, but that's not what I expected. If you show that, I think we would just split that because for unsorted bin, it's first in, first out, rather than first in, later out. So it would first check the huge one and split it.
Why would you check the huge one first?
So he's saying a stack versus a queue. And that's because we are freeing the big one right here before the small one. So it is last in, first out.
Can you run the command chunks? We'll see the result. Chunks or
You want right here chunks.
or what's the command?
I don't know what you want me to show you. So chunks.
Can you check small bins? I don't think that there would be.
Like it did what I thought it should do. I'm not sure what you're thinking should happen.
Yeah, can you check the small bins?
Or can you keep bins?
Oh, that's interesting. I'll double check that. I'm wrong.
That's a surprise.
And what happens to the rest of that bigger chunk? Did it get thrown back into all of this, or?
Oh, well, where was it? Where did this thing come from?
Oh,
We snapped off what we needed, and then
right,
just,
because it's still malloc, so or rather the malloc part of malloc. So
right. The malloc part got what it wanted and was like, "Hey, man, we're good. We're out."
Okay.
Right. So we.
Okay, so the rest of it just gets left and unsorted bin. It doesn't go anywhere. It doesn't get sorted anywhere else.
Correct. And if there were more chunks that were in the unsorted bin that we hadn't evaluated, those would also still just be chilling there, right? Because it's all about, malloc is all about being quickly returning what you want. And so we only dig through the unsorted bin enough to satisfy whatever it is that we're asking for. And so here we broke it off. And if there were smaller things, we're like, I don't care. I got what I need. We'll dig through the garbage later.
So what happens now when we free the 1,000 bin bytes we allocated?
Okay.
Where does it go now? Just go straight to unsorted, or does it just run?
Let's free 14.
Yeah.
Okay, we did the thing. It looks like it consolidated.
T-cache, doesn't it? Is that 1,000?
Oh, because it was small enough. You're right. Yeah, it was small enough to go into T-cache.
Yes.
But what also could have happened, so if it was big enough to avoid T-cache and avoid fastbin, then it could immediately consolidate with this guy right here. Right? But our sizes weren't large enough to cause that to happen. Right? And so there's this interesting thing you can do, which is what the first couple levels kind of focus on, or try and get you to play around with the concept of, is what if I need to force a pointer from like a large malloc to return a specific address, but you can only malloc small things. Well, you can do the math here because the heap is deterministic, right? I can fill the T-cache, and as long as I'm dealing with things that are larger than fastbin, I can force things into this unsorted bin, and I can even force things in the unsorted bin to consolidate such that they satisfy the requirement for a larger malloc, even though I'm working with smaller chunks. And you can do the reverse as well with big chunks and weird kind of math with your offset here. And so this entire module is just about juggling things and forcing things through here. Now, in the T-cache module, we said there was heap metadata, right? Well, there's heap metadata here too, and it's going to look very similar to, that's a lame one. Give me a cool chunk. Is this a cool chunk? I don't like your heap chunk command. It's going to look very similar to what we have seen already, where there is a size, a next pointer, and then there is also a previous pointer. I picked something that was in T-cache, so it doesn't have that metadata. The large bins have two additional pointers, which is next size and previous size. So like with the T-cache and fast bins, everything is a fixed size, right? Everything is hex 80 bytes. But for the large bins, it's a range. And the reason that it has those dual pointers, do I have anything in large bins right now? No. Is because what happens if I malloc something like 12 things that are the same size that go into the large bin? It would be every next pointer would point to each one of those 12 things. What if there's a 13th thing that goes into the large bin that's twice as large? As a performance optimization for navigating that list, I'm not going to go next until I find the thing that I want. Instead, I'm going to go next size. because it's going to give me an allocation that is in the range of the large bin, but is a different size than the current chunk. If you want to graphically see that, the official documentation right here, although their numbers are also not large enough for large bins, we see if we have two things that are the same size, like size 132, size 132, the forward pointers are just going to follow everything that qualifies in this range for the large bin, right? And so what if there's like 100 things of size 132, but I really want to get to that chunk down there at the end that's 120. I don't want to go next 100 times. So they have this additional pointer that is forward and backwards for the size within the range of that large bin. So I can skip the 100 chunks that are all size 132 and just get to the next smallest size.
Do those pointers only exist at the first one of those, or are they duplicated across all those chunks of that size?
That is a good question. I believe it exists in all of them. Right? Now, there's no reason for it to be needed here, right? From a usage standpoint. So they could be adding it. It's a good question. We don't have time to find out. They could be adding it when malloc is called, right? They could be going next, or it would be forward next size equals my current next size at the point of malloc, right? And so I don't know if that's part of when they unlink it and pull it out, or if it's written every time. I know in the lecture slides, I treat the metadata as if next size or forward and back size pointers exist everywhere. They really only exist for large bins. It's just when you think about the metadata as a whole, I find it helpful to just be like, this is how things are. All right, and the last thing in my 2 minutes is how to heap. So I said this whole module is a giant troll that says use some advanced heap exploit. Right? We spent this entire time poking around at GDB and looking at how things shuffle around. What you'll want to do is run the challenge and say, okay, what do I have control of? Right? Can I malloc big things? Can I malloc small things? Can I put things in the fast bin, in the small bin, in the large bin? Figure that out and write it down. Write down what your capabilities are. Right? Then go to this repo here, Shellfish How to Heap, which is linked right here. This is not like an optional tip. This is like a mandatory if you want to try and solve this tip. This repo is maintained by KyleBot on the Discord. And it is a list of heap exploits for various libc versions. What version is the dojo running? 2.3.5. So we want to look here. It will matter. Now, these are all different style of heap attacks, and they typically have cool names, right? Like House of Spirit, House of Force, House of Water, right? I don't remember where those came from. It's kind of like a historical artifact. And these are all proof of concepts, like where's House of Spirit? People always say they do House of Spirit, and then very rarely do they actually do House of Spirit. I find that to be the case. People on the Discord are like, I did House of Spirit, and it's like, no, you didn't. You corrupted some metadata. This is all written in C, and so you can SCP this up and compile it and run it on the dojo. It exploits itself, right? It is not a run this and it defeats a challenge, right? It shows you, if you were to compile this and run this, what is the memory layout that is necessary? What metadata are you corrupting, and what is happening? And so it is useful. House of Spirit is when you create a fake chunk and then spirit it from nowhere into existence to then all of a sudden have a pointer that didn't exist. It's a cool exploit. But what you'll want to do is you'll want to look at what you have control of in the challenges, and then look at these proof of concepts and understand kind of what's going on. And you're going to need to implement what you see going on here in C inside of your Python script to exploit the challenge. Every single one of them, every single one of the challenges in this module are inspired strongly by something on this page right here. Now, not all of them are used. And in many cases, there is only one correct answer, right? So if for instance, you can only do super small allocations, maybe we want to start looking at the fast bin, right? Because that's the only bin we can interact with. So then we'd say, all right, well, what's going on with the fast bin here? Well, here's something that says fast bin. Let's take a look and see how that works. Can I apply the logic that's demonstrated here in this challenge? And that's kind of the methodology for going through this. With that, I am out of time. People just laugh at me being a fool. It's always good. Does anyone have any last-minute questions?
Office hours this Friday, as usual?
Office hours this Friday, as usual. I will show up if you show up. That is the deal. All right. With that, I will leave you all. I appreciate you all hanging out. I'll see you on Friday.